Demystifying neural network optimization. Shedding light on the black box. While dealing with big data, a modern neural network is significantly more flexible and expressive than a conventional linear model. Yet for many practitioners, deep networks remain an enigmatic black box. How does the optimization algorithm discover the millions of weights and biases that yield high predictive performance in the first place? When you fit an ordinary least squares regression, you do not search for the coefficients, you solve for them directly. The closed-form normal equations ingest the data matrix and analytically return the unique best-fitting parameter vector. Run it repeatedly on the same dataset, and you will obtain identical coefficients to the last decimal place because the global optimum was analytically predetermined. This is estimation by formula. However, no such closed-form solution exists for neural networks, nor will one ever be found. The composition of nonlinear activations renders the loss surface non-convex and mathematically intractable to invert directly. Consequently, we rely on estimation by search, initializing parameters with random weights and iteratively refining them until improvements plateau. If you have estimated a logistic regression via maximum likelihood, you have encountered this paradigm before. Iterative optimization is simply scaled in deep learning to millions or billions of parameters, transforming search dynamics from an implementation footnote into the core discipline of machine learning. Defining what wrong means. Objective and loss functions. Before a model can be systematically updated, its performance must be evaluated through a scalar metric known as the loss function. Selecting this loss is a fundamental modeling choice rather than a mere technicality. For regression tasks involving continuous outcomes, the default standard is mean squared error, MSE, which averages the squared residuals between predictions and ground truth. Classical statisticians will recognize this immediately, since minimizing the mean squared error is the same objective that underlies least squares regression. What changes is the root to the minimum. Least squares reaches it in closed form, while neural networks approach it iteratively. And therefore regression analysis is not considered a genuine machine learning approach. For classification tasks, the standard choice is cross-entropy loss. To build an intuition. Imagine a forecaster predicting a 99% probability of sunshine right before a downpour. Cross-entropy penalizes this overconfident error far more severely than a cautious 55% forecast. The penalty scales exponentially with unwarranted confidence, enforcing calibrated probabilistic outputs. Cross-entropy is also mathematically equivalent to the negative log likelihood in binomial logistic regression, highlighting another direct convergence between classical statistical theory and modern deep learning. The optimization landscape and the gradient. A foundational mental model for optimization is a hiker navigating a high-dimensional valley blanketed in dense fog. The hiker's altitude represents the loss, her coordinates correspond to the current parameter weights, and her objective is to reach the lowest possible elevation. Lacking global visibility of the terrain, which in modern architectures spans millions or hundreds of billions of dimensions, she must rely entirely on the local slope beneath her feet to identify the path of steepest descent. This local slope is the gradient, the vector of partial derivatives of the loss function with respect to every weight in the network. Functionally, it operates as a comprehensive sensitivity analysis. For each individual weight, the partial derivative answers. If this parameter is nudged upward infinitesimally while holding all other parameters fixed, how does the loss change? The full gradient points in the direction of steepest ascent. Therefore, parameter updates move in the exact opposite direction. Calculating these partial derivatives by perturbing each weight individually and evaluating the entire network across the dataset is computationally impossible, requiring millions of forward passes per single step. Deep learning resolves the computational bottleneck through backpropagation. Backpropagation is not an optimization algorithm in itself. It is an exact, highly efficient credit assignment algorithm or an accountability system. Rather than estimating parameter sensitivities via brute force perturbation, backpropagation computes all partial derivatives simultaneously in roughly the computational cost of a single backward pass. At its core, backpropagation is the chain rule of calculus framed as an organizational accountability report. Consider an institutional decision, such as an automated credit or customer churn prediction, passing through multiple tiers of intermediate representation. When a prediction deviates from reality, such as the network underpredicts churn probability, the resulting error signal is generated at the output layer. For a standard probabilistic classifier paired with cross-entropy loss, this error signal simplifies cleanly to the raw difference between the predicted probability and the true outcome. First, activation scaling dictates that the gradient with respect to any incoming connection is directly proportional to the activation level of the upstream neuron. An intensely active neuron that contributed heavily to the erroneous output receives a substantial parameter adjustment, whereas an inactive or dormant neuron receives zero update. Silence earns neither credit nor blame. Next, local gate modulation governs how error traverses the hidden layers, where the signal is scaled by connecting weights and multiplied by the local derivative of that layer's activation function. For example, a rectified linear unit, ReLU, transmits the error intact when active, but completely zeroes out the gradient when inactive. If a neuron remains unactivated across all training examples, its parameters permanently freeze, a failure mode known as the dying ReLU problem. Finally, layer-wise compounding determines how effectively error signals reach earlier representations. In deep networks utilizing saturating, S-shaped activations, such as sigmoid or 10H, the activation derivatives are strictly bounded well below unity. As errors multiply across successive layers, the gradient decays exponentially toward the input layer, the classic vanishing gradient problem. Modern architectures mitigate this bottleneck by adopting piecewise linear activations and residual skip connections. Because backpropagation evaluates layer-wise products in reverse order, from output to input, it systematically reuses intermediate derivatives computed at higher layers. This dynamic programming approach avoids redundant calculations and provides the exact gradient required for parameter updates. Optimization dynamics, learning rates and batching. Once gradients are computed, the parameter update adjusts each weight in the opposite direction of its gradient, scaled by the learning rate. The learning rate dictates the step size along the loss surface and remains among the most critical hyperparameters in model training. Setting the step size involves a critical trade-off between stability and speed. An overly aggressive learning rate causes the optimizer to overshoot local minima, inducing severe loss oscillations or numerical divergence. Conversely, a conservative rate produces glacial convergence or causes optimization to stall prematurely in plateau regions. A related consideration is the choice of batching strategy, which determines how frequently parameter updates occur. Calculating gradients over the entire dataset via batch gradient descent yields exact directional accuracy, but it becomes computationally prohibitive on large datasets. At the other extreme, stochastic gradient descent, SGD, updates weights after every single observation, which is fast but introduces extreme variance. Modern practice converges on mini-batch gradient descent, which computes gradients across manageable subsets, typically ranging from 32 to 512 samples. This approach provides a computationally efficient directional estimate while introducing beneficial stochastic noise that helps the optimizer escape shallow saddle points and sharp suboptimal local minima. Advanced optimizers. Momentum, RMS prop, and atom. Standard mini-batch descent encounters structural challenges in anisotropic ravines, lost surfaces characterized by steep walls along irrelevant dimensions and flat gradients along the optimal path. This causes oscillations across the walls rather than steady descent along the base. To address the challenge of ill-conditioned ravines, Momentum equips the optimizer with velocity by computing an exponentially weighted moving average of past gradients, typically with a decay factor of beta as 0.9. Under this formulation, persistent gradient directions reinforce one another while high-frequency oscillating components cancel out, dramatically accelerating traversal along the base of the valley. Separately, standard optimization assumes a uniform learning rate across all parameters, which penalizes rare features whose associated weights receive infrequent updates. RMS prop resolves this disparity by maintaining an exponentially decaying average of squared gradients for each individual parameter and dividing each update step by the root of this running average. Consequently, frequently updated weights with large historical gradients are damped, while rarely active weights receive amplified, compensatory updates. Adaptive moment estimation, ADAM, synthesizes both approaches by tracking a moving average of the gradients alongside a moving average of squared gradients, incorporating bias corrections for initial zero settings. With default parameters, beta 1 equals 0.9, beta 2 equals 0.999, learning rate equals 0.001, ADAM serves as a robust baseline across diverse domains, though empirical evidence demonstrates that well-tuned SGD with momentum often delivers superior generalization in computer vision benchmarks. Statistical guarantees versus empirical generalization. It is instructive to contrast deep learning optimization with classical statistical inference. In classical OLS regression, the estimator guarantees a unique global minimum alongside valid standard errors, exact sampling distributions, and rigorous hypothesis tests under Gauss-Markov assumptions. In contrast, gradient descent on non-convex neural networks offers no global optimality guarantees. Multiple training runs initialized with different random seeds will converge to distinct parameter coordinates. However, extensive empirical and theoretical findings demonstrate that in heavily over-parameterized regimes, high-dimensional local minima and saddle points exhibit remarkably consistent generalization performance. Nevertheless, minimizing empirical training loss is merely an instrumental proxy. The ultimate objective is out-of-sample generalization. It is relatively easy to build a model that retrospectively explains patterns in data we have already observed. The real test is much harder. Can the model make accurate predictions for new, unseen data? Consider a hypothetical example. Suppose I develop an economic theory that beautifully explains the Panic of 1873, the Great Depression beginning in 1929, the 1987 stock market crash, the 1997 Asian financial crisis, and the 2008 global financial crisis. Will I earn the Nobel Prize in economics? Probably not. I have shown that my theory can explain the past. Now let us see how well it anticipates the future. If it can successfully predict the conditions associated with the next major financial crisis, then people will really start paying attention. People might even start following my advice on when to invest in the stock market. Of course, I have not developed such a model. If I had, I probably would have retired 20 years ago. An over-parameterized network possesses sufficient capacity to memorize noise. Consequently, robust training pipelines couple gradient-based optimization with structural regularization, cross-validation by data partitioning, early stopping, weight decay, and dropout. The big picture is therefore surprisingly simple. Forward propagation makes a prediction. The loss measures how wrong it is. Backpropagation determines who contributed to the error. The optimizer adjusts the parameters. Then the network tries again. Neural network learns by repeating that cycle, sometimes millions of times. I hope this illustration helps you understand how neural networks learn. From now on, when people complain that your AI output results from an opaque black box, you can show them a confident smile and explain the underlying mechanics step by step. Thank you for watching. See you in the next video.